let's see.
Okay, maybe we switch just for a
Yes,
second.
because I don't
you
know.
take this. Yeah, no, we look live. Okay. Yeah, there's lots of thumbs up.
Okay, so if we need to check if somebody hear me.
Yeah. So maybe we can ask if can someone in the chat let us know that you can hear us? That would be amazing. Yeah. Just so that we know that we're not talking to ourselves. Let's turn this around so people can see us, but it's a bit close. Okay, yes, perfect. Okay, we can hear. So let's get started.
Okay, welcome to this live from the Atlas underground cover. This is rather exceptional because we were not supposed to be able to come here, but today we are allowed. We cannot go very close, but we can still go around and show you around. So it's two of us that we're gonna guide this tour. My name is Marcella, and
hi, my name is Clara. So we both work on Atlas, and we're working in different areas. Can you say a little bit about your research?
Okay, so I work in two main aspects. On the more technical side, I work on what is called a trigger, which is the hardware and software that allows us to filter and select the event we're interested in. And then I work on physics to a couple of aspects. In particular, for example, I can say that I work in looking for dark matter signals that could, in principle, in our condition, we could create dark matter, and we want to try to see if it is the case.
Brilliant, yeah. And so, I said my name is Clara. So my main research is on the top quark. So this is the heaviest particle that we've discovered in the CERN model so far. And it's particularly interesting because, as Marcella was just talking about dark matter, it might help us to uncover dark matter because its mass is so high and the way that it interacts with the Higgs boson. This is this brand new particle that we discovered here at CERN in 2012. It might give us hints of other things that are happening in the CERN model when we understand this relationship and also just study the top quark in depth. So this is my main area of research. I also work on the detector itself for many years. So my job was to design new radiation-hard pixel detectors. So these are the parts of the detector that are very close to the collision point, and because they're so close, trillions of particles pass through them. And that means that they can get damaged, and therefore we want to make sure they last as long as possible in our detector. So that was what I was working on for many years. So I'm going to hand over to Marcella just for now. Maybe you can tell us where we are at this moment, and I'm going to go through a detector.
Okay, very good. Thank you. Okay, so we are 100 meters underground. So if the camera can go closer to this,
Well, if we just wait one moment, sorry, this is what I wanted to check ourselves.
Okay, so we are 100 meters, about 100 meters on the ground, and here below me we are at the top of the Atlas cavern. So you see that here this green part is closing from the bottom the shaft, and so 100 meters above us you will have the surface, and then this cavern is about 45 meters long and about 25 meters, more than 25 meters high. Now this is basically all filled by the Atlas detector that we're going to show, but you can see a glimpse already of the external part. Now the Atlas detector is really the biggest at the Large Hadron Collider, being 25 meters high. Now 25 meters, especially if you see it here, is not clear how big it is. But if you think about a 9-story building, you understand how impressively high is this thing. In fact, you'll see a little bit the floors inside the cavern. on the here on the side. And so this is the entire size of Atlas. Now Atlas is the biggest, so because of the technology that we chose, especially in the external part of the detector, and which is what we're going to see mostly, because of course now Atlas is ready to take data, and we're just pausing the data taking for some weeks now. And so it's ready to take data, so it's completely in what is called a closed position. And because it's a closed position, we only see the external surface, okay? So Atlas is the geometry, it's a classic detector geometry.
This isn't working, so we just have to talk very loudly.
Okay, it's a classic detector geometry, so that basically you have your collisions, and then the particle produced in the collision will go in all directions. And so what we really want in a detector is we want to have layers around the collision point in order to capture all the particles wherever they decide to go, whichever direction they decide. And so ideally you want to have something that really encloses completely the collision point. And from the engineering point of view, the best solution is having a cylindrical form and then discs closing both sides. And so what we're going to do, that we're going to see, is that every single layer of material that is making up our detector has this cylindrical and disc-like form. And there are different layers because different layers have different material, are made of different material, and they are seeing different particles and measuring different properties of the particles. And of course, people are welcome to write questions, and I'll interrupt, of course. We're here for your question making. So the main idea is of this onion-like structure where you have these different layers, and we can simplify the structure by having three main layers. And so the first two, there's no hope that we can see because they're really deep inside this onion, and only the third layer we can glance at here because it's the external part that we can see. And the first layer is what Clara has been working on, and basically it's just a way to really see the particles, see the traces, the trajectory they do going through layers of silicon pixel or strips. So the silicon pixels are the same that are in your cameras, on your phones, and listen electric signal. So it means that you have a lot of points because of all the layers of the silicon, and basically you can draw a line that goes through this point, and that is the actual trajectory that the particle has gone through. And this is the smaller, the one that is really closer to the interaction point, because we really need to see the traces of all the particles that are coming out. And the additional information that we get, which is really, really important, is that we also can put these silicon layers in a magnetic field. And if we do that, what happens is that because of the effect of the magnetic field, the traces of the particle, instead of going straight, they will make a bend, a curve. And this is the radius of this curvature is proportional to the momentum of the particle. And the momentum of the particle is one of the fundamental properties of the particles that we want to measure. And so by just like looking at these geometrical traces, we have a fundamental property of the particle. The momentum is the mass times the velocity at the speed. So it's really characterizing what the particles that are coming out. The second fundamental property is
So sorry, it's a science in action.
Technical advancements are happening.
So just hold it like that.
Okay.
We don't want
Okay.
to, yeah, like that.
Okay, is it working?
So we're going to see in a moment if that's any better.
Okay. Okay, so I was saying that the second property that we want to measure is the energy, and the second layer is what does that. And these are called the calorimeters. And basically, again, the principle is rather simple. You have a very thick material, and you want the particle to stop within the material. If they stop within the material, it means that they've released all their energy. They pass all their energy to the material. And we are able to choose materials that will allow us to retrieve this energy via light, via photons. And so we collect this light, and this light corresponds one-to-one to the energy of the particle. And so this is our second layer that measures the energy of the particle. And then the third layer is somewhat special because it focuses on the one particle, one of the particles, but the main particle that we cannot stop, and they will just go through the whole layers, and that are the muons. So now muons are heavier cousins of electrons. They are rather normal particles. They're not very exotic. We have muons going through us all the time in cosmic rays, so they are common, but they're not in normal matter. Okay, and so when they meet normal matter, they don't interact too much, and so they can travel a lot. And so we have a third layer just to measure muons. And so again, you have lots of layers. The muon go through, leave electric signals, and you can have the trajectory of the muons that are coming out. And those are very important also for my work from the point of view of what I was mentioning earlier, because we need to have a way to filter the information, because LHC gives us 40 million collisions per second, and we're not able to save them all. And at the same time, we're not interested to save them all, because not all of them are very interesting collisions. We want to select those collisions where the two protons really crash into each other. And so that doesn't happen all the time. And so we need to have a way to select from the control room up there, 100 meters up above, which are the interesting one. And a muon coming out from the collision point is a super good signal to tell us this is a good collision, you really want to save it. And so that's why muons are also very, very important. There are other reasons, of course. Do we have any question?
Oh, okay, we have a question about pixel tracking.
Oh, yes.
Okay.
You got it.
Yes, how you distinguish particles that hit the same pixel?
Ah, excellent question. So yeah, we have a question, so I'm just going to repeat it for the stream. We have a question saying, how do you distinguish between particles that hit the same pixel in the detector at the same time, I guess? So that's really tricky. We have teams of people who are trying to work on this, to try and work on the tracking. If a particle passes through one pixel at exactly the same time as another, then it's very difficult to distinguish that. We can a little bit know that there was more charge because we measure how much charge was deposited in that pixel. But the main way that we would do it is by looking at the other pixels that have also been hit at the same time, because we have multiple layers of not only pixel detectors, but also strip detectors and further on in the detector itself. So we would then track back the paths, and we could essentially draw a line between all of the pixels and the parts of the detector that were hit. And we could say, okay, it looks like two particles crossed at that point, and then the reason for that higher charge in that pixel was because there were two particles at the same time. But so really it's about the tracking rather than individual pixels that are hit. Excellent. I think what we could do now is maybe take a look down. So we have to be careful not to drop our camera over the side, but if we come a bit closer, and just tilt it over because we're very high up right now. So the lift is actually not working because our magnet is on. So we climbed 11 stories to get up this high. So we're on top of the detector. And I know that Marcella was talking about the detector itself. Did we also talk about the dimensions in the cavern? Yeah, perfect. So we already have that while I was checking on the sound. So yeah, we're very high up right now on the top, and this is the muon sector, the muon spectrometer that Marcella was talking about. And right now, what we're showing above the detector, what's in the center of our image, is the Large Hadron Collider. So this blue part is the accelerator itself. So you can see this, really large blue section. And the reason that it's so big is because we have 2 beam pipes within the Large Hadron Collider. These are for the proton bunches that are going in opposite direction. And then around that, we also have a dipole magnet, which bends the path of the charged particles, not in every section of the LHC, but in a lot of the LHC. And then we also have cooling because the magnets in the LHC go down to 1.9 Kelvin, which is 1.9 degrees centigrade above absolute zero. And so because they're so cold, we need to isolate them from the room temperature environment that we're enjoying right now around us. So the reason that they have to be so cold is because they are superconducting, and superconducting materials at the moment, it's been discussed in the news quite a lot at the moment, but the ones that we use have to be cooled to very, very cold temperatures. So we can pass it on. So
There are some questions, I'm told, but I cannot see them.
I'll bring them up on my phone, it's easier. Yeah.
Okay.
And open up the iPad in a minute.
Okay, just 1 second that...
Question about what upgrades does the LHC receive?
Oh, for the LHC?
Okay, so for the next... so up to 2026, we're gonna run steady. So keep taking data in a similar way as in the past. We increased a little bit the energy, but not in a very significant way, but still it is interesting enough, especially from the point of view of the when we look for very rare processes. So it's very interesting to accumulate more data, and having a little bit more energy is always good for us. Then in 2026, we're gonna have a long, it's called the long shutdown, and that would allow us to both upgrade the detector and upgrade LHC. And the upgrade is going to be to have a higher intensity of beams. So not necessarily going to higher energy, but higher intensity. And that would allow to take more data in the same time. So the higher is the intensity, the higher is the number of collision, the interesting collision we get. And so if at the same time we upgrade our detector and we increase our ability to record collisions, then we're gonna have a lot more data from 2030, let's say.
Yeah. So one of the questions we do have is, what is the number of collisions per crossing of the bunches? So right now we have, here, do you want me to take this? I can give you that.
Yeah.
So right now we have on average about 60 at the beginning of what we call a fill. So a fill is when the Large Hadron Collider is filled with protons, and then we can start colliding with stable beams. And at the beginning we have a maximum average collisions of about 60. And this is actually set by Atlas and CMS in that we request it from our accelerator colleagues. And that is because, as Marcella was just saying, we do have limits on the detector, and this is the optimal operating parameters that we have right now. When we have the upgrades, so as you were just describing, we could, for the high luminosity LHC, go up to 200 collisions per bunch crossings, and that's going to be a massive challenge for our detectors, but we love a challenge, so that's what we're working on right now in order to be able to work with that amount of data. What I recommend, you have another question?
Not finished.
Well, what I recommend we do is that we could maybe move down a couple of levels, because you found quite a nice platform we could stand from.
Yes, true. But I have a.
And you could
meanwhile,
talk as
yes,
we walk,
okay.
maybe.
There are two very interesting questions.
Excellent.
Wait a second that I read it. Okay, so based on the energy and charge distribution and doing statistic hypothesis tests, we can differentiate between two particles. Okay, so this is very interesting. This is exactly, so let's go down in the meanwhile. So that's exactly what we do. Basically, what I was saying was that we measure momentum and energy of the particles. And then we statistically, but also specifically, we put together this information, and we put together we also know where in the detector this information have been gathered from, and then we can match in this. We do what we call particle identification. So yes, exactly. So we put together the information. We say, okay, this looks like an electrons, and then statistically we assign. Based on the measurement that we did, we assign a probability to that statement. And we say this is a 68% or 92% probability to be an electron. And then based on that, the analyzer can decide which quality of a statement of statistic they want to use. But in general, we do exactly that. So we put together the information, and we learn about exactly which particle was created. There was another interesting question about dark matter.
Oh, there was a question about how you find dark matter.
Right.
If it doesn't interact.
And I think you got the right idea, like seeing gaps in the detector. So the general idea is that when we have... that's a good background.
Setting up the scene.
The idea is really that. So we basically know all the particles that are coming out that we can see. We measure their energy, and basically we can do an energy balance. And if we find this energy unbalanced, it could be that a particle that we didn't see has taken this energy. Now there could be a lot of particles. So in general, we can do something very generic, saying, okay, if I'm missing a lot of energy in my accounting, what can it be? We can, and then we can just have a generic, what is called a independent search. So just for new signal that we don't understand. Or we can go and talk to our favorite theorists, and they will come up with crazy idea that could work, and that we can test. So we can go and say, okay, my theorist friend has an idea of a new particle that would behave like this and this, and so that I can actually go and test their ideas. And there's no shortage of crazy ideas, of course.
Yeah.
But in general, we want to really check all the possible imbalances in the detector. Does it make sense? But the question was talking about gaps, which is exactly the idea, yes.
Yeah. And maybe I can add
Yes.
on top of that, because, for example, machine learning has been discussed quite a lot. So often in public media, it's called AI. In our research, we call it machine learning because we're training the algorithms to learn, but it's not autonomous right now. It's not doing anything on its own. It has to be guided and trained. But we use this quite a lot. We've been using it for 20 years at least in particle physics, to be able to separate what we would call a signal, so the interesting part of the process that we're looking for, from the background, which are other events that are not what we're looking for. And also, just for clarification, the background for my analysis could be the signal for someone else's analysis. So it's not completely uninteresting. It's just not what, for example, I'm looking for at that moment. But we use machine learning to help us isolate these specific processes in the data. And we're also, as Marcella was talking about dark matter in these general searches, we're starting to use machine learning to search for things that as she was saying, theorists haven't necessarily predicted yet, but that just look different in our data, because by using machine learning algorithms, we can allow it to process multiple different properties of the data at once to try to look for things that don't match our simulations, which come from what we're expecting in the data. So I wanted to add that in since we were talking about dark matter. So it's one of the ways that we're searching for dark matter, and we look for it in multiple different ways in order to be able to find it if it's hiding in our data. So right now we're on floor 9, as you can see behind me. So we've got a slightly different view of the detector. This is the muon spectrometer that we mentioned earlier. We can still see the Large Hadron Collider. And we're not going to be able to see any of the subcomponents that are within the detector because it is closed up. As Marcella was saying at the beginning, but I'm not sure if you heard with the microphone, this is a really special time that we're able to come underground. So we took the opportunity to be able to show you the detector in this way whilst we can. Because the LHC is just having a couple of minor repairs at the moment, which allows us, while the LHC is not running, to come underground and do this live tour. So I think you've got another question.
There are lots of questions.
Excellent.
First of all, more data means we will be more confident to suppress the noise background data, right? Yes.
In general, yes. One thing that is interesting to note, that if we have more of these collisions happening at once, then we have more of what we call pile-up. And pile-up are just other events that are happening during the one that we're interested in. And this creates challenges for our detector, for our data acquisition for the trigger. It creates challenges for sorry, I lost my train of thought. Yeah.
Okay, so then I'll ask you the other question, which is very fitting.
Okay.
So then how do you deal with this pile-up of so many collisions in one event?
So that's a great question. So one of the ways that we deal with it is, for example, the detectors are what we call, they're granular. So when you upgrade your phone from a 10 megapixel to a 50 megapixel, if you've got a 50 megapixel camera, that is also what we do with our detectors. And that's having more, in the pixel detector cases, more pixels in order to be able to separate those signals out. But we also have many software improvements that we are developing. So again, we're using machine learning to be able to separate the different signals we see in our detector. And we're also designing upgrades for our detector. So when we go from the current pileup of about 60 to 200, we're completely reinstalling our inner detector. We're going to have a whole new pixel and strip detector that's going in there. We're also designing a component called the high granularity timing detector. So this is going to go in around the calorimeters in our detector, and it's going to be able to help us know when the particles arrived in the collisions as well. We do have timing information, but it's going to give us more precise timing information, and that's also going to help separate these different processes out. So that's one of the ways is that we use the detector, and the other way is that we're really using better algorithms. We have so many of our colleagues are improving these algorithms that we use to distinguish the different particles as they pass through. But it is a challenge, and it's a challenge that our accelerator colleagues give us every time they upgrade the LHC. Then we are kept on our toes, and we're upgrading our detector and our software as well.
Okay, so I see. What is the hot topic of the current research? Dark matter particles?
Yeah.
It's one of the. I'd say that the dark matter searches are rather. We rather focus on dark matter because in a way it's something that we know it's out there. We know that we know that in the from the cosmological measurement from the galaxy movement there is something. There are different hypotheses. We don't know what dark matter is. It could be particle. If it's particle, so we already have chosen one path, okay? If it's particle, then it's natural to think that we would produce it here. And there are lots of theory, lots of models, lots of ideas from the crazy theorists I was talking about before, that will incorporate what is called a dark matter candidate. So even if they are made with a lot of particles, new particles that we could find, in particular, they mostly have a dark matter candidate. So we can test these theories and also try to find a possible solution to this dark matter mystery, because we don't know. However, we need to keep in mind that dark matter could be not particle in nature. So it's if you want, it's an excuse to address a fundamental problem, but at the same time is also a way to find whatever is new that we are producing, even if it's turns out if we have a new signal, it might not be dark matter, but it's okay. We're gonna investigate and find out what it is.
Yeah. I mean, we also have another important part of our research is the precision measurements that we're doing. So it's not just about searches. Often people talk about the Large Hadron Collider as a search machine, and they say that because we use protons for our collisions. Now, protons are very messy because they contain quarks and gluons inside of them. And this means that we never know exactly, even though we know exactly what energy we're accelerating the particles to. So at the moment, when we're running, we collide to 13.6 TeV, center of mass collisions. Because the proton is made up of internal particles, we don't know exactly the energy that those particles collide at. But that means that we have a whole spread of different collision energies which create all these different particles that exist in nature but that aren't hanging around that we want to study. So it is a search machine, but we've done so many precision measurements with this detector that are allowing us to understand the properties of the particles that we've already discovered in even more detail. So for example, the Higgs boson, we discovered it in 2012, and now we're really testing every single one of its properties to see if it's matching what the standard model predicts. So we want to know exactly what its mass is. We want to know how likely it is to interact with other types of particles. Because, for example, we have 3 generations in our leptons and quarks, in our fermions. So we want to test the Higgs boson interacting with each of those generations, and is it interacting at the same rate? Because what could happen if there are new particles or forces or processes that we haven't discovered yet, that could be it could affect our measurements. So the Higgs boson might not change into muons as often as we think it should, and that would tell us something interesting was going on. So these precision measurements are really important to also test the standard model, and we've put out over 1,000 papers since we've been collecting data with the Atlas experiment. So we've had loads of incredible results come out in the last many years.
So I have a question that is linked to what you were saying about the Higgs boson and how it's connected with dark matter, and there's been a little bit some replies already, but the bottom line is that yes, it could be even the portal particle, so a particle that connects the dark sector with the standard model, so the particle that we already know. And then another question that you might know nicely: what machine learning algorithms and models are most currently used for particle reconstruction and identification?
I mean, the most popular one right now are neural networks. It used to be what we called boosted decision trees, but now neural networks are really the most favored type of machine learning. But we really, we branch out and try a lot of different types as well. So for example, graph networks have been used. Unfortunately, we don't have time to go into loads of details here in this talk, but there are lots of machine learning experts. And in fact, I'm going to give a plug because we have many excellent live talks that we have done on our channel. So you can go through those, and we have a whole talk on dark matter, on many of the particles that we study, and so you can check those out for even more detail if we don't answer it today while we're in the tunnel. What I'm going to do is I'm going to
I want to ask you another question. That was nice. Do
Okay.
you prefer? You prefer to measure something that supports the standard model or that conflicts with it?
I think every particle physicist is going to say we want to find something that disagrees with the standard model.
We agree.
Yeah.
We agree.
I mean, yeah, it's a fantastic theory and it is held up so well, but it doesn't explain everything in our universe. It's what we call incomplete. It doesn't include gravity. It doesn't explain why there's more matter than antimatter in our universe. It doesn't tell us what dark matter is. And so there must be something else in our universe. And in fact, I'm wearing the Lagrangian for our standard model right now on my t-shirt. This is the short version from the CERN shop, which I picked up recently. But it's incomplete. And so we want to break it. We want to find something else that's going on as well. I'm going to hand you back the microphone because what I think we should do is go and find another view.
Yes,
of the
let's
detector
go
to
and
look
find
at.
another view. So there was a question about phaser, which I don't know much about.
A little bit about
Okay, but we cannot show it because it's not in this cavern. So there's no way we can show it because it's a very forward detector, right? So it's a forward detector. That means that there is a special tunnel that continues the Atlas cavern and is able to collect the residual, the particle that you can generate in the Atlas cavern, but that escapes. So it's basically long-lived particle, I assume.
Yeah, that's what it's looking for. So I have a colleague at my institute who's working on this and another friend who's working on it too. So really they're looking for dark photons, for axions, for these sort of dark matter-like particles that could be being created in our detector. But as Marcella was telling you earlier, and as was asked in a very nice question, they leave a sort of gap in our measurements. And so what phase is looking for, because these would be neutral particles, they wouldn't be carried along the Large Hadron Collider beam pipe along with the protons, which are charged. They would go straight down this special tunnel, as you were saying. And so they put this detector phaser down that section of the tunnel, and they've tested it out already. So they measured neutrinos. It's the first time that neutrinos have been directly detected from collision events. So it was that was an achievement on their commissioning of the detector, and now they're collecting data in order to be searching for these dark matter-like particles. So it's a really nice addition to the program that we have here at CERN. We really try to use as much of the space and the infrastructure as possible to search for things in as many different ways as possible. So we're going to keep walking because I want to get a few levels lower, I think would be nice. Yes. You want to see if there's any more questions that we can answer on the way. What can I tell you as we're walking? So when we get one more level down, we're going to have a bit of a closer look at this muon spectrometer here, because the nice thing about being in the tunnel is we can get really up close to the detector. So if we, Simran, if you can go a bit closer there. So here on the right, this is part of the muon spectrometer as well. They're called drift tubes. So we've got a point there. And these tubes are, part of the muon detector. And they work by having a gas inside of these tubes and then a wire inside the center. And when a muon passes through, it releases electrons in that gas, which are then collected by the wire. And then, as the name suggests, it drifts along those tubes, and we collect the charge at one end, and the time it takes to collect that charge tells us roughly where it was located. And because we're so far away from the collision point, that is good enough for us to know where that muon has gone. And because there's a number of them, we get a number of hits. This really improves our measurement. And so this is just one part of the muon detector that we can see really up close while we're here. And also, if you tilt the camera up all the way, where you can see that green and gray section, usually when we're not running, that is completely open to the surface. So we're about, I would say about 50 meters underground right now, about 40. The detector itself is 25 meters high. So yeah, somewhere around
I think 93 is the
bottom. Yeah,
So we're about minus 80.
minus 80. Yeah.
Here maybe minus 70.
But yeah, when we're running, we close off that. It's one of the access shafts we have underground. And it's how we built this detector here in the cavern. Because it's so huge, we really used all of the space available to us in this cavern. And what we had to do is lower the pieces in bit by bit and then construct this detector in situ to be able to run it. And we often say it's like building a ship in a bottle. And if you want to see how this works, we also have a video on our channel of when we upgraded a section of the muon spectrometer that you can't see, unfortunately, because again, we're closed up ready for data taking. But it looks similar to this big one that we have behind me. But we call it small because it's 10 meters in diameter instead of 25. And it just fits through that access shaft. So we lowered 2 new ones down. We'd already taken the old ones up. And these were improved muon spectrometers that we had constructed in our collaboration in order to improve our data taking specifically for muons. And that was a huge undertaking. It was completed in the last long shutdown for Atlas. And yeah, we were really happy that they went in and they're working brilliantly in our detector. We have a...
Okay, so they're super funny questions. So there's been a little bit of off topic on the neutrino masses.
Okay.
So neutrino masses, we cannot do anything about it. We cannot really measure. We cannot measure directly neutrino. We cannot do any of the measurement that we would like to do on neutrinos. For this, there are other experiments. So, for example, just Google Super Kamiokande, for example. That is an experiment in Japan who's been taking data in the past years. And you see this super tank of water with lots of phototubes around. And there they can see the interaction of neutrinos with the water. And then they also see how the neutrino changes from one type to the other, and that's called the neutrino oscillation. And that's our evidence that neutrino have a mass. However, this mass is so small that we cannot quite measure it. We haven't been able so far to measure it directly. There are methods, but they imply a control, a very, very precise control of everything else, basically, and it's called endpoint, like one of the methods, and to try to see a small signal that is different from what everything else gives. There are methods. We're not getting there just yet. But there are other experiments looking into that. And then there was a little bit of discussion about, I forgot now.
Well, my favorite comment that I saw was set phaser to stun. So, I like the nerdy humor. And what I recommend is we keep walking again.
Yes.
We're going to keep going down to another level.
Okay. There was another question, but I forgot. A discussion about... the sound, right? Yeah, that was also interesting. So,
there was a question about do we compare our results to CMS?
Yes, so that's that one. That is something that I can answer, unlike the sound, which I I don't know what to say. We want to go here? No, we cannot go here. Okay. Okay. So yes, we do compare. So CMS is the other general purpose detector, how we call it. So we do the same thing in general. So we have different technology, different people, different detector, but the idea is exactly the same. So we are able to see the same thing, and we're trying to measure the same thing. And so what happens is that we keep our results a little bit hidden and secret. But if there is something that is new, that is a new particle, for example, we would pick up the phone and talk to them, to CMS, to see if they have the same and if what they have is similar. Because we want to cross-check each other. If there is an amazing new signal, new particles that only Atlas finds, then it's possibly that nobody will believe Atlas. And so we need to confirm that CMS sees something similar. And so we really need to talk to each other. So we need to be a little bit secretive because we want the analysis to be independent. So I have a very good friend. She works in CMS. We do the same thing. We talk about what we do, but not too much. Not because I don't want to share it with her, well, a little bit, but in particular, I want to develop my analysis in an independent way. She has to do it independently, and then we compare ideas and results, and that is how it's a true cross-check of each other, and that's why we want to make sure to. So now we are in level 4. Are we? So we are exactly at the level of the beam. So if you look there, then you have the beam pipe, the one that we were seeing from above. And so basically inside that shielding, there is the beam pipe. The beam pipe will be, I think, less than 20 centimeters in diameter.
It's about 10 centimeters. Well,
here is a little bit bigger. Yeah. Okay, so the normal beam pipe would be about this size, but in the LAC. Here, when we have the two beams that are in the same beam pipe, it's a little bit bigger, but not much bigger. And then this is the shielding to protect the beam pipe from the rest. And then this is called, I don't know if we said it already, this is called the big wheel. Yeah. Because of the shape, in a way, of the wheel, but sometimes people ask, can it turn? And sadly, it cannot turn. And it would be a big problem.
Yeah. If it turns, we're unhappy.
Yeah. So, no, it doesn't turn. And so here, like, you also see an immense amount of cables that are coming out of from the center, because we're almost at the center of the cavern. Yes.
So here's a really nice view. Thank you very much. So yeah, here's a really nice view of the detector side on. So it is symmetrical. So if we went about 40 meters in that direction, then we would end up with the same view. I'm just going to put my device on the floor so I'm not dropping that. So here this is the muon spectrometer. And the reason that we have this gap is again for measuring the muons. We really take advantage of most of the size of our cavern, and we have this wheel of the muon spectrometer out as far as it will possibly go, and then as the muons travel, it allows us to more precisely work out what their track is. And then I saw one of the questions in the chat about the gold plates on the muons. Have you worked on the muon spectrometer directly? So I mostly work on the inner detector, but these plates are also used for the triggering. Their purpose is to help us more precisely know the time of the arrival and quickly measure that out, so that then the trigger experts, and when we say trigger, it's data acquisition, it's the people that are collecting the signals in our detector so that we can measure those out and collect that data and analyze it later.
So I have a few questions. So I'll start from the last one because it works well. So most of what you see is made explicitly for this detector. So we do try to get commercial pieces like boards and elements, but it's very hard. Like Clara was mentioning the radiation hard aspect. It's rare that we can find elements that you buy commercially that would support the amount of radiation that we have here. And so most of the time there is a specific R&D done at all the levels, and then we try to build our own. Now, the scale of Atlas is so big that we possibly are doing a mixed strategy. So some we design ourselves, and then we try to have them manufactured by industries and so on. In the past, there were smaller experiments physicists were building everything. Now the scale is so big that we were forced to go more at the industrial scale. But it's still a little tricky because our requirements are so high in terms of precision, in terms of quality, that the general industry it struggles a bit in keeping up.
Yeah, but it's actually a really, it's one of then the advantages of CERN is that we're designing these components. It's one of the most tricky environments that electronics have to be in on the planet. And so we're custom designing these detectors to be able to work in this environment, but we're working with these industry partners who then get to learn from what we're doing. And it's the way that the different countries that are involved with our research get to benefit from the technological advances that come from this kind of research. Because we don't patent anything in terms of restricting it. Everything that we do here at CERN is open access and openly published. And that means that companies can directly make use of this research and these advances. So the technology that we have in our detectors, like in Atlas and in the other detectors we have here on the LHC, have been used in PET scanners, so positron emission tomography scanners used in hospitals to see inside the human body for medical applications. There are also similar devices that are now on the ISS, on the International Space Station, because they have to deal with the radiation that's coming from outer space. And they need electronics that are going to be reliable in that environment too. So they're using some of our detectors to monitor the radiation that the astronauts are exposed to. And yeah, it's used in a lot of different situations. So we have a lot of what we call transfer of technology from what we're doing here at CERN. I saw one of the questions early on in the chat was the purpose of this detector just for measuring the particles that are created. And yes, in our case, that is what we're interested in. We want to know how our universe works on the very, very smallest scales. But the technology and the advancements that we make are shared in other situations where they then can be used for medical technologies, for high radiation environments, that kind of thing. We also have, and this isn't to do with Atlas, but we have our own fire brigade here at CERN, and they are specifically trained. They come from all over the world, and they spend time here at CERN to be able to learn how to do their jobs in a radiation environment. I mean, it's not radioactive here right now, but for example, if they needed to get down here right after the LHC was running, they need to know how to do that safely. And it means that they can then take that knowledge back to their countries as well. So there's so much sort of opportunity to understand this environment and then take it back and apply it in different situations.
Okay, there are a few questions.
I'm going to suggest we walk and talk again, because we're getting close-ish to the end of this live. So please make sure you put your questions in the chat now. If you're watching this later, if you're not watching live and you're catching up with us later on our YouTube channel, then please still put your questions down in the chat, and we'll get some of our colleagues to come and pass by and answer those questions later, or we'll be able to answer them on our other social media channels as well. So make sure that you still put your questions in, and we'll try and get those answered at a later date as well. So I'm going to hand you back the microphone. We're going to head down now to the ground floor, I think, and we're going to look up at our detector from that beautiful vantage point. And then answer as many questions as we can before we close, but we do have to eventually leave the cavern because we have a safety officer who is monitoring everything here at CERN. It's because we are in a restricted environment. This is a cavern, so that means that it's a closed environment with limited access tunnels. And so we have someone above ground who is watching us right now, very kindly taking care of us and making sure that we're absolutely safe. We're sure that we are, but it's nice to have someone watching. And we've got to let them go home at some point and have their evening, have some dinner. So yeah, we're going to walk down to the ground. Do you want me to? I don't mind walking and talking this time if you want. Yes. But do you want to give me one of the?
So the question is, what about the danger of producing a mini black hole?
Oh, thanks so much. Yeah, let's talk about that as we walk. So this was a big question, a big discussion item when we first turned the Large Hadron Collider on. We know that creating anything that would grow to be massive cannot happen in our detector, and we're very confident about that because of these collisions that happen in our atmosphere. So very highly energetic particles are created in our atmosphere. They collide, with our atmosphere, and this has been happening for billions of years, and it's been happening all the time, all over our atmosphere. So we know that what we're doing here with the Large Hadron Collider is completely safe in that aspect. There was a discussion about miniature black holes, and we also know, for example, if those were created in our atmosphere, they cannot have a very long lifetime, otherwise we would have observed them happening in our atmosphere too. So then they would what we call evaporate. They would fizzle out if they were created. It is something that we check our data, and it would be interesting to see if that happened, but it's not a danger, because if those types of micro black holes were created, they would evaporate and fizzle out. So we already know.
Probably would see a signal with a lot more particle than normally. So they would create a collision with a lot more particles. So we would, our trigger will pick it up, and we would look into that. That would be really cool.
Yeah, but also, I mean, many of us are living here, spending all of our working days at the detector, and so we're all very confident that it's completely safe to be around the collisions. In fact, our control room is like 50 meters above the collision, or 100 meters above the collision point. So we're going to keep going now down to the ground floor and see the detector from possibly my favorite angle. I always, every time I get to come underground, I marvel at the fact that I can come and see this detector, and this gigantic experiment that was created by thousands of people who all came together from all over the world. We have over 100 different nationalities here in our Atlas collaboration. So it's a truly global effort to get this done. And then we create something like this huge detector that is able to study our universe on the smallest scales imaginable. It's almost mind-boggling that we have to have something so big to measure something so small, but it's because of the energy levels involved. And so, I think this is possibly one of my favorite places to view the detector from, because you really get to see the whole thing as much as we can fit in a camera. So
I think this is very good, because it links to another question that I saw earlier about how far the particle travel, and this detector is exactly created for exactly the energy of the particle and the type of length of travel they will go through, and so the size of the detector is to allow the first two layers, so the calorimeter, to stop. So we know that most of the particle will stop in the calorimeter, so they will travel a few meters, and then everything else is at the external of the calorimeter is only the muon detector, and the muon detector is made so big because of the innovative idea of Atlas. So muons will go rather fast, let's say, and so you want to see the curvature of the trajectory to measure the momentum, as I mentioned at the very, very beginning. Now, in order to measure this curvature nicely, it's better to have an expanded, so the layers should be farther away, so that you give the time to the muon to bend, okay? And that's why we have an expanded detector, okay? The solution, for example, the CMS got is put iron between the layers, and so the muon are losing energy by going through the iron as well. And so they made a compact version of a detector because of this different technology. Okay, and so this is the main idea. And this linked also to another question about calibration, and because of course, if you have all these detectors that are in air, you need to calibrate them regularly. And so we have a cycle of daily calibration that to make sure that we know exactly where each detector is, and we are able to connect the points as we were mentioning earlier. Do you see anything?
So I mean, this kind of links to what you were just saying. So there was a question saying the detector is so huge, so doesn't those metal shielding block the particles from arriving to the detectors? So it's something that, maybe I can... So it's something that we're very careful about close to the interaction point. So for the inner detector, we can't prevent it entirely. So we do still need to have structures to hold the detectors, and also for the cooling, because we cool the detectors to different amounts depending on what's needed for them to operate most efficiently. But some particles are interacting with that structure, and it reduces what we call the resolution, so the amount of information we're able to get about those particles. But we try to reduce it as much as possible.
But for example, the structure of the inner detector of the part that is small, that is closer to the internal the collision point, is made of carbon fiber. So if you it's a super light structure, and that is exactly to not disturb the particle as much as possible. Here we are at the end, so we can be a little bit sloppier, I guess.
Yeah, also what's really interesting is the beam pipe. The LHC beam pipe is made of beryllium, and this is a compromise between having strong tensile strength, so being able to keep the vacuum inside of the LHC beam pipe, whilst also having a low interaction level with the particles that are passing through. So we have to compromise. We have to do the best that we can in order to have the support structures, the cooling, whilst minimizing the interactions with the particles.
Can you come with me so that?
Oh, sure. We can go this way. So one thing. Oh, okay. Can you hold this? One thing I do want to quickly do. Do you want to introduce yourself quickly before we go? So I'm going to give. Because we also have Simran who's training with us. If you hold the full thing so it's not dangling.
Yeah. Hi, I'm Simran. I'm a PhD student. Also in Atlas, also looking for dark matter and supersymmetry. I work as well on one of the detectors, so I'm more often down here to fix things, but now I'm training to be also a virtual guide and show you all Atlas maybe the next time.
Excellent. And so Simran's been our excellent camera person today, so thank you so much for joining us on this tour. So yeah, maybe we can go around just to this part, because it's another great view of the detector. Do we have any more questions before we...
Precision of alignment of the detectors.
So, we can use the muons that we've been talking about, these ones that come from cosmic rays. When we're running the LHC, we have to account for these in our measurements. We have to remove them from the data. One way we can do that is the fact that they travel, generally in a straight line, not from the collision point, but say from above down, or whichever way they've come through our detector. So it's pretty easy to remove them, but they cause an extra additional challenge for our understanding of the processes. But when the Large Hadron Collider is off, they are then incredibly useful for us to be able to calibrate and align our detector. So what we would do now, for example, not quite now because it's almost dinner time, but what we would be doing while the LHC is not running is turning on the sub-detectors anyway and measuring the charge of those muons passing through. And this, because they also travel in a very straight line, except for when our magnet is on, but we can use that to precisely know where every part of our detector is. So that's something that we can use. And then also, I guess, when we're running, the muons that are coming from the collisions can also be used for some alignment as well.
I think the level of the precision is between micron and millimeter, depending on if you look at inside or outside. I don't know the level of the muon too much, but I would think that's what you need in any way. Yeah.
So how are we doing then for questions? So we will have to wrap up soon and close this live. Do we have any last minute ones that are coming in?
I don't know, a neutron flow. I'm a little bit confused by a neutron flow.
I think
you can create a wallpaper from this view. It's a good idea.
I'm going to embarrass myself, but I think that's a Star Trek reference. I should know. I'm a bad geek.
I don't get that. Oops, I'm not. not geek enough. That's bad.
Maybe you can tell us very quickly if we've completely misremembered
Do you
whichever.
still collaborate with the Russian Institute? We have we are in intermediate phase where there is an ongoing treaty that is going to end at the end of 2024. Okay. And we're going to see what happens at the end of 2024. But at the moment, I think that the idea is that we don't want to punish the Russian scientists because it's not their fault, most of them. They're not involved. And they are good collaborators, so they will get their names on the paper, but we're not going to quote the institutes. And so that is the current strategy. Sorry, I'm slow.
Yeah. So we oh, it's a Doctor Who reference. Thank you so much. And I should know that because I love Doctor Who. But yeah, sorry.
I'm so sorry. Yes, sorry.
Yeah.
We need to study.
I watched Stargate, so that was my favorite.
No, I started Doctor Who when I moved to UK, of course.
Yeah.
I mean, that's what you have to do, right? To get the citizenship.
It's on the test.
Clearly.
Yeah. Great. So I think we should. We got some last.
There's another one. Does the cavern get radioactive when the LAC operated? Yes. When it operates, we're not gonna come down. And it gets radioactive, but is a radioactivity that is linked to the beam, as you mentioned. So as soon as the beam goes away, it goes back to normal level, even below the surface. Because of course we are 100 meters underground, so the radioactivity level here are lower than on the surface.
Yeah.
We're safer here.
Yeah, because of all the rock and the concrete.
We just stay here forever.
Yeah, there's no coffee down here though, so.
Okay, I take it back then.
Okay, I think we're going to have to wrap up now because I think we should also head back to the surface despite being protected from those cosmic rays and allow our colleagues to have their evenings. But thank you so much for joining us. Thank you for all of your questions. They've been fantastic, kept us on our toes, which is excellent. We hope that you've enjoyed seeing our amazing detector. I find it a privilege every time I get to come underground. So we've been very happy to show the detector to you while we've been down here. Simran's giving us some.
I think it's my first time in restricted access, so it's very, very privileged. I feel.
Yes.
Yeah. Thanks a lot for all the questions. They were and sorry if I hope we could keep up with them. It's not an easy task. We found.
But we can try and go back through it another time. So if you didn't get your question answered, please go through the comments, come back to our video, post them in the comments, and we'll try and get them back. And just to let you know, the reason that we haven't gone in this direction, where you can see my finger pointing, is because our toroid magnet is on. So we don't want to get too close to that while we're down here. So as Marcella said, it is restricted access. So you're very lucky that we were able to show you this view. So any final words?
Bye, everybody.
Yeah, bye. Thank you so much for joining us. And I'm going to press the button.